as said earlier, we will be talking about negative temperature and see that how it arises in a system, at least in the transient phase of the system. As an example of the canonical ensemble, we will do ideal gas, and also we will do all these other systems such as Einstein model of solids, in which he tried to explain the specificity of solids, especially at low temperature. In this context, we will see that these the model of solid is nothing but a collection of oscillators, quantum oscillators, and how this gives rise to specific heat in the canonical ensemble. And then we will do a spin J system. We have done a spin half system, that is paramagnetism of a spin J system. There is a Brillouin function comes, and that in the limit of large temperature gives rise to the Curie susceptibility, and we will also do equipartition theorem. So, let us start looking at negative temperature. So, the thermodynamic definition of temperature is, so this is a thermodynamic definition. Is nothing but T equal to del S del E inverse at constant n and v, and 1 over T equal to del S del E. So, at constant n and v. So, there is no guarantee that S of E, S as a function of E, that is the entropy as a function of energy, is a monotonic function of E. In fact, no law of thermodynamics is violated if S is not a monotonic function of E. Now, suppose S is a monotonic function of E. Monotonic means that it sort of varies in this fashion. So, S versus E is like this, and the slope is always positive. In that case, temperature is always positive, but there are instances, or there are examples in which S is not a monotonic function of E. And for that, to show that, let us consider that we have there is an example, and there are n non-interacting spin half particles in a magnetic field. Okay. And suppose in this situation, to begin with, the initial condition is that, or initial scenario is that all the spins are pointing in the direction of the magnetic field, and in which case the number of microstates is just 1, that is, all of them are pointing in the direction of the field. So, they are pointing, say for example, up direction, assuming that the magnetic field is in the upward direction. So, this gives a log of omega, which is log of 1, which is equal to 0, and that tells us that the entropy of the system is 0, and it is easy to understand that all the spins are pointing up, and there is no disorder in the system. So, it is just in a very ordered state, and this should give us the entropy to be equal to 0. Now, you change the magnetic field, and how you can change the magnetic field? Let us consider a solenoid. So, this solenoid is just a cylinder or a tube with either it could have a core inside, that is core of a magnetic material, or it could have a simply vacuum inside. You have a number of windings of the wire which carries current, and say the current is being carried from left to right, then the magnetic field that is generated inside the solenoid, assuming that it is large and we neglect the edge effects, then this is given by mu 0 n into I, where mu 0 is the permeability of the medium inside, capital N is the number of turns, okay, and I is the current that flows. And now, what you can do is that you can change the direction of the current from left to right to left, and in which case you will change the direction of the magnetic field in this direction. Okay. So, that tells you that the magnetic field direction is not difficult to change, and suppose at this moment just assume that you have kept this spin half particles inside such an arrangement where you have a constant magnetic field, and that can be reversed. Okay. So, what will happen is that all the spins cannot respond immediately to the changing direction of the magnetic field. So, a few will turn towards the magnetic field and slowly everything will start pointing towards the magnetic field again, and if you wait for long enough, so change direction of the field and if you wait for long enough, then all the spins will now be pointing down, assuming that it was initially pointing up along the direction. The field direction was up and the spins were also pointing up, and now the spins are pointing down because the magnetic field is pointing down. So, again we get a situation in which the number of microstates is equal to 1. So, S let us call it as the initial and let us call it just I, and S f the final is again equal to 0 because all of them are now pointing in the same direction. Now, alternatively you can think about it that in this ordered system, the initial ordered system, when there is all the spins are pointing along the direction of the field, you pump an energy say mu 0 b, okay. Then one spin points flips, okay. If you do it 2 mu 0 b, 2 spins will flip, and if you apply an energy n mu 0 b, then all the spins will flip. So, we are not talking about changing magnetic field, but we are just saying that you pump in energy to the system, and again the system goes from entropy equal to 0 to entropy equal to 0, and in between it has a finite entropy. And if you want to know how the plot looks like, then the plot looks like pretty much like this. Sorry about this energy. Okay, same here. Okay, so this is a energy axis and this is the entropy. So, this is S as a function of E and this is E here. Now, you see that there are two regions, let us call it A and B, or it is denoted by blue and red. In this blue region or the left half of the semicircle, the temperature is positive because the entropy grows or entropy increases and energy increases. But however, so this is the initial position when all the spins were pointing say in the upward direction, and this final situation, let us call them as maybe O and O prime. So, at O all of them are pointing in the same direction, that is upward direction, and you have these energy to be entropy to be equal to 0. Then you are pumping in energy to the system, mu b, 2 mu b, 3 mu b and so on, the entropy rises, and this is a situation, this quite strange, because this situation would tell you that 1 by T, which is equal to del S del E, which is equal to 0, because the slope it sort of saturates and the region becomes flat, and if it is flat, then the definition tells you that 1 over T equal to 0, that tells you that this is T equal to infinity, and this T equal to infinity really is not infinite temperature. It just simply means that the number of up spins is equal to number of down spins. Okay. And then the right half of the semicircle sort of starts showing a decrease along the red line, and where the temperature is negative because the slope of this del S del E curve is equal to 0. But you see one thing here, the negative temperature region, which is given by or rather denoted by B, is hotter than the region of positive temperature, and this tells you that so it is really a transient, because the heat or the energy will actually sort of go from the higher energy state to a lower energy state, and this negative temperature state would cease to exist in an equilibrium scenario. But nevertheless, this is an example where the statistically the entropy shows a negative slope with respect to energy, and you have a negative temperature arising in this region B. Now, this is of course an idealization, or rather it is a thing that is always possible to arise, but whether is it really true, or is it possible to have this kind of state in experiments. So, let us ask this question, that how realistic it is. So, we have already said that this is this negative temperature region is hotter than the positive temperature region. So, let us call it as hotter, and we know that hotter body or the hotter region in some parameter space, there will be change in energy or change, or rather exchange of energy or exchange of heat to a less hot region, and eventually it will come to an equilibrium. So, one thing that can be told about how realistic it could be, that we are only talking about the spin degrees of freedom, okay, where we have just not considered anything else, but these are collection of spins. Now, that of course is not a realistic situation. The spins have to be carried by someone, say they have to be carried by the fermions or other things, or even bosons and so on. So, not spin, bosons are not spin, but let us talk about just fermions. So, if we include other degrees of freedom, there is no guarantee that your entropy would be a non-monotonic function. So, if you look at this, this looks like that it is like a two state system. I mean, this is an important understanding that we gather from here, that here the energy is equal to minus say mu 0 b, and this is say plus mu 0 b and all that. So, energy is bounded between these two values, which are like minus mu 0 b and plus mu 0 b, okay. Or you can write this mu 0 is called as a Bohr magneton, or the magnetic moment of the system, okay. So, this is really for a bounded system, or you can say that it is a two state system. So, this is negative temperature is only possible, which we have made clear earlier also, that S has to be a non-monotonic function of energy, and this is one of the examples that it can be a non-monotonic function of energy, okay. So, if you include other degrees of freedom, then S of E may not have non-monotonicity. I hope it is clear what I mean by non-monotonicity. It means that it sort of goes up and then comes down. This is called non-monotonic behavior. A monotonic behavior is just as we understand from the word, that there is a sort of boring increase in one direction, okay. So, here in this particular case, S is only an increasing function of energy. Now, it is also very important to realize that when we talk about this, how realistic it is, that whether we can operate an engine from negative temperature to positive temperature, okay. And this will answer this question, that whether if we can do it and get physically meaningful result, then that means that second law etcetera everything is valid and we have a physical situation. But it is not possible to operate an engine from negative T to positive T. Let me tell you how. If you remember, the efficiency is given by 1 minus Q2 by Q1. We have done this earlier, 1 minus T2 by T1. And just to remind you that Q1 is the heat absorbed at temperature T1, Q2 is the heat rejected to a temperature say T2. Okay. In an usual scenario, T2 is greater than T1, okay. And that tells you that eta is less than 1, which means the efficiency is less than 1, and this is what the statement of the second law is all about, at least this Clausius statement and other statements that have been put by Carathéodory and all that. So, this tells you that the maximum efficiency of an ideal engine has to be 1, but any realistic engine will have Carnot engine will have an efficiency which is lesser than 1. But now what happens is that if you have these temperature to be negative, so then this T2 is greater than T1. So, if the T2 is greater than T1 and which tells you that for negative temperature. So, this is like a negative temperature scenario. What I mean by this is that the from a hotter region to a cooler region, you are trying to operate Carnot engine, then eta becomes negative and can become very large. Okay. And this and can be large also. Now, this has important implications that instead of work being produced by the engine, you actually have to do supply work to the engine in order to keep it running. Okay. And in terms of the second law, this means that it is possible to extract heat from a cooler body and transfer it to hot bodies. Okay. So, that is not possible by the statement of the second law. Second law of thermodynamics. Now, as I said that even though it is not possible to have it realistically, but it is a transient in some kind of a non-equilibrium situation, this is still possible to achieve, and which is what we have given this example of the spin system, one can achieve that. Okay. So, now this negative temperature is, let us just stop at that for the negative temperature, and let us carry on with examples of canonical distribution. And we will do a number of important examples. Let us start with classical ideal gas. So, this is our favorite system anyway, and we know that either the energy or the Hamiltonian is written as sum over I and P I square over 2 m. There are no other degrees of freedom, only kinetic degrees of freedom, which is half m V I square, which can be written as P I square over 2 m. We have taken that all the masses of the particles are same, but you can take this to be m I and it does not matter. Okay. So, it is this is the energy of the system, and if you have to calculate the partition function, then what we do is that we will integrate over all the positional coordinates which are like this, and we will have to do the same for the momentum coordinates, but this will not be independent because we have a term in energy which is like this, and there is a d cube p n, and this is exponential minus beta, and so this is like a p I square by 2 m. A little better way of writing could be that each one of the terms we write it as d cube p 1. So, there is a sum here which we should write. So, which means exponential minus b, this is 1 beta p 1 square over 2 m, then this is cube p 1 d cube p 2 e to the power minus beta p 2 square over 2 m, and so on, and then you have a d cube p n and e to the power minus beta p n square over 2 m, and so on. Okay. This integral gives you simply a v to the power n, each one is v. So, there are n terms. So, it is v to the power n. This from all these integrals from minus infinity to plus infinity gives you a Gaussian integral, and keep this in mind all the time because we need it very frequently in statistical mechanics. It is minus infinity to plus infinity dx is equal to root over pi by alpha, and at times we actually also would need from 0 to infinity, in which case we have a half factor coming in front of this. So, this tells you that this is nothing but equal to, it is a v to the power n, and so here it is alpha, which is what we have said there. So, alpha is equal to root over 2 m by beta. Okay. So, we have a root over pi as well. So, this is like a 2 pi m by beta and whole to the power half. Now, there are sort of all of these things. So, all these there are 3 n of them, and or rather let us say that there are n such terms. So, we write it as v to the power n 2 pi m by beta to the power n by 2. Okay. This actually is should be written as a little more carefully, one should do it, because this is a one dimensional integral that I have done. So, this is like a dp e to the power minus beta p square over 2 m is simply equal to 2 pi m by beta to the power half. Now, if you do it for dpx, dpy and dpz, you will get each of these factor as half, and then it becomes 3 by 2, and since we are doing it in 3 dimension, we are getting a 3 n by 2 here. You can also do it like this, 4 pi p square and e to the power minus beta p square over 2 m 0 to infinity dp. This will also give you the same result. It's just that if you need to know what this thing is, then what you do is that you take a d2 d alpha 2 of this expression or this integral minus infinity to plus infinity e to the power minus alpha x squared dx. So, it is a d2 d alpha 2 root over of pi by alpha, and then do not forget to replace a half there, because we for 0 to infinity we have it. So, this is actually from 0 to infinity. I mean minus infinity to plus infinity will be this, and if you want a half of that, which is 0 to infinity, you just multiply it by half. So, the partition function for a classical ideal gas is given by v to the power n and 2 pi m by beta whole to the power 3 n by 2. So, for n particles. Now, what is it good at? You can get simply equal to minus k T log z, that is the Helmholtz free energy, and that can be processed here, and we can write this down as v to the power n, and we have a 2 pi m over beta whole to the power 3 n by 2. Now, there are two terms. So, log of say for example, a and log of this is a b. So, we can write this as minus k t log of so this n will go up, I mean will come in the front, and we have a v, and then we have a 3 n by 2 log of 2 pi m by beta, and so on and so forth. Now, this part is not important at this moment, because we want to get the pressure. So, and we can, if we want to get the pressure, which means that we want to derive the equation of state, and so this is equal to minus del f del v, with n and t to be constant, and this is nothing but minus n k t log of v. You take a derivative with respect to v, that will give you this 1 over v. Now, there is a minus sign here, and then there is another minus sign here. So, it will become plus, and so we recover the very well known ideal equation of state, or rather equation of state for ideal gases, and which is P v equal to n k t. Okay. So, starting with particles which only have kinetic energy, writing down the total energy of the system, calculating the canonical partition function, we get at a given temperature, we recover the equation of state. So, let us do the next example to be equal to, say for example, the one dimensional oscillators. Let us call it as an Einstein solid, and I will tell you what is Einstein solid. But before that, let me just do the classical oscillator without attaching too much of importance here, but it could be important in some other situation, not in the present one. So, the energy of an oscillator, which we can write, we can also write as a Hamiltonian. So, if we write this P to be and X to be as operators, so it is half m omega square x square. Okay. So, if we want to know the partition function, so we have to it is like minus infinity to plus infinity e to the power minus beta m omega square x square by 2 dx, and minus infinity to plus infinity to the power minus beta p square by 2 m into dp. I am doing it in 1D. Okay. So, but it can be trivially extended to 2 higher dimensions. So, each one of them is this Gaussian integral, and we can do this, perform this integral and so on. So, this for one particle in one dimension. So, let me write it as z1. So, this is equal to root over pi by alpha, where alpha is equal to 2 divided by beta m omega square. So, this is equal to root over beta m pi omega square divided by 2. I hope I have not made a mistake here, but you use this relation that we have. So, this is the Gaussian integral that we have talked about, and this is anyway root over 2 pi m by beta, and then we can multiply. So, z1 becomes equal to root over beta m pi omega square by 2 into when you do the integral, it will be 2 divided by beta m omega square, and that is what we have written. Pi over alpha is root over 2 by beta m omega square. You can see this and convince yourself that if there is anything wrong that has been done here, and then you just multiply it by 2 pi m by beta and so on. Okay. All right. So, this is just check this thing. Okay. All right. We will do a quantum oscillators for Einstein solid. And what do we mean by quantum oscillator? Now, there is something subtle here. We are applying a classical statistics or the ensembles to a quantum mechanical problem. We just simply take the result of the quantum mechanical problem. So, in a way it is still doing classical statistical mechanics, but on an energy spectrum which comes from quantum mechanics, and this is given by E equal to n plus half h cross omega, where omega equal to k by m, root over k by m, where k is the force constant or the spring constant and m is the mass. So, the model is like this, that I am just drawing it in one dimension, but you can generalize it to two or three dimension and so on. So, these are the atoms and ions, and they are connected by springs. So, these are capable of vibrating about their mean positions, and the vibration can have all degrees of freedom, that is the longitudinal and transverse degrees of freedom. If you solve the Schrodinger equation corresponding to a Hamiltonian, which looks like a minus h square by 2 m d2 dx 2 plus half m omega square x square, it is like a parabolic potential. So, the potential that one has is like this. So, this is the v of x versus x. So, this is this term. So, this particle is actually confined in this parabolic well, which means that they have only harmonic degrees of freedom, and there is a model for a solid, and that is what he visioned it, that it could explain this specific heat of solids, and he was nearly correct, excepting that he made a mistake, which we will talk about later, that this vibration about these atoms or ions about the mean position will correctly give rise to the lattice specific heat, or which is called as phonons, because these excitations of these atoms or ions about the mean positions are called phonons. And so, one has really a potential like this. So, if you expand the potential about the mean position, you get a x square kind of behavior, and this is very successful in sort of describing a solid. However, it cannot, it has also demerits, it cannot explain the melting of solids, which means that in this harmonic approximation, this is called as a harmonic term. So, it is a harmonic potential, and within this approximation you cannot explain the melting of solids, which requires your average value of x, which is equal to 0 within these the wave functions. However, I mean that should not be 0, in fact that should diverge as the solid starts melting. So, the harmonic approximation is good for something, but it is not good for some other things, which we accept anyway in physics at various places. Now, these are the energy spectrum. We do not need anything more at this moment, but just it is good to know that the wave function for this quantum harmonic oscillator in one dimension is some constant, and it is multiplied by sort of polynomial, and there is a Gaussian of this form. Okay. I am writing it without normalizing it, without any other prefactor, but it's these are the essential elements which tells you that this polynomial has a certain property, that is when n is even polynomial, that is even in x, that is if you change x to minus x, it does not change sign, and this is the Gaussian that you are familiar with now. So, this h n of x has a property that it is even for even n and odd for odd n, which means for odd n, if you change x, it will change sign. Anyway, this part we do not need, just it is good to know. So, we calculate the partition function for this quantum harmonic oscillator, this also has an important implication. This n can actually take values 0, 1, 2 and so on. Okay. So, 0 is a possibility, and the 0 gives you a 0 point energy which is equal to half h cross omega. So, even at absolute 0 there is some 0 energy that is possible, and we now want to calculate the partition function, canonical partition function. So, let us just write it as there are n oscillators. So, n quantum harmonic oscillators, that is the system that we have, that is at each lattice location there is an atom or ion which behaves like a quantum harmonic oscillators. So, this is equal to sum over j from 1 to n, and we have n j plus half h cross omega. Let me write it a little cleanly so that later you can take it. So, we have let me write it here, n non-interacting quantum harmonic oscillator. Oscillators. Okay. So, these are the energy of that, and we need to calculate the canonical partition function, which is nothing but equal to now this n j, and there is an exponential minus beta e, and this e is a function of n j. We will just write it as that. You see, and n j can take values, sorry, this is I mean this j will take values from 1 to n, but n takes values from 0 to infinity, okay. Anything it can take. So, this is the quantity, or rather this expression that we have to calculate in closed form, and that is not difficult to do it. It is easy to see that this canonical partition function is of the form, there is this n j exponential minus beta sum over j equal to 1 to n, n j plus half h cross omega. All right. So, there is a double sum that you see, this j goes from 1 to n goes from 0 to infinity, and so the double sum again factorizes nicely, and we can see this, that it is equal to, for each j, that is j from 1 to n, this gives you the same result. So, we will just take a raised to the power n. So, this is from 0 to infinity, and exponential minus of n plus half beta h cross omega. If you wish, let me write it with and this is the total partition function, and we can write it as z 1 to the power n. So, which means that this identical partition function for all the n oscillators, okay, and we just have to calculate one of them and then raise it to the power n. If we can calculate it in a closed form, that is what will serve the purpose. Okay. So, this is equal to nothing but so if you write a few terms here, let me write it here. So, for n equal to 0, it is exponential minus beta h cross omega by 2, n equal to 1 is 3 by 2 beta h cross omega plus exponential minus 5 by 2 beta h cross omega, and so on. Okay. So, you see this is like a GP series geometric progression, with the first term being beta h cross omega by 2, and this is 1 minus the common difference, which is exponential beta h cross omega, and this is exactly what we would write, is exponential minus beta h cross omega by 2 and divided by 1 minus exponential minus beta h cross omega. Okay, we can write both of them. Okay, let me write this as e to the power minus, just to have a, it looks nice top and bottom. All right. So, this is the partition function, and we wanted to have it in a closed form, which we have got now. Now, let us write the free energy, which is per particle. So, F by n, that is equal to this is minus 1 over k T, this is 1 over n log of z. So, this gives you this is equal to half h cross omega. So, this is k T log z, okay. And this we can just divide it by n. So, we have this log of z, and anyway this is a z1, your z is equal to exponential minus beta h cross omega by 2 1 minus exponential beta h cross omega whole to the power n, and you can do this, calculate this thing, which gives you half h cross omega. So, what we do is that we take a log of z, and then there are the exponential there, and remember that log of exponential x is equal to x. Okay, and we have here log of exponential minus beta h cross omega by 2 is equal to minus beta h cross omega by 2, and so on, and then there is a log of 1 minus this. So, which can be easily simplified, and we get a k T log 1 minus e to the power, okay, let me write it as e to the power minus this is h cross omega by k T. So, we write beta as 1 over k T, just to have the temperature dependence explicit in this expression. So, there is a free energy per particle, and what would be the entropy after this? The entropy is again, so entropy per particle, per particle means per oscillator. Okay. So, this means oscillator, just that we are more used to using n to be number of particles, it is actually oscillators, and this is equal to S, which is equal to a minus del f del t, and this is equal to minus k log of 1 minus exponential minus h cross omega by k T. These are simple derivations, does not make sense for to work out each and every step, but for your benefit you should work out each and every step, because it is also very easy to get lost in this bit of algebra that you see here. So, it is h cross omega by k T, and this is exponential minus h cross omega by k T divided by 1 minus h exponential minus h cross omega by k T. Okay. So, this is S as a function of T. So, there is the entropy as a function of T, and specific heat again per oscillator or per particle. This is, let me write it with a small c, this is equal to T del S del T, and I will write down the result, but you should work it out. It is h cross omega by k T whole square exponential h cross omega by k T exponential h cross omega by k T minus 1 square of that, and that is the specific heat, and one can actually calculate the limiting cases, that is t going to infinity and t going to 0 are the two limiting case. That is this is called as a classical limit, and this is the quantum limit. Okay. What one gets is that in the limit of so what you have is that you have the ratio of the two energy scales h cross omega and k t, or you have to compare between the two. So, h cross omega by k t to be much smaller than 1, this means that t equal to infinity limit, and this is like classical, and for the other one it is h cross omega by k t to be much greater than 1 when the quantized energy of the phonons or of the oscillators that dominates, and hence it is a quantum limit. Okay. And this internal energy of the system can also be obtained. So, what you can do is that instead of using this C equal to T del S del T, you can also calculate the internal energy, which is minus 1 over n. So, internal energy, which we write as U energy. Now, this is of course per oscillator or per particle. This U is equal to minus 1 of 1 by n del del beta of log z. So, you can directly get the internal energy, and from there, and this is nothing but equal to half h cross omega plus h cross omega by e to the power h cross omega by k t minus 1. Okay. So, in the limit of large temperature, when h cross omega large T is much smaller than k T. So, what you get is you can do this when h cross omega is much smaller than k T. You can write this as the second term as h cross omega, and this is like exponential x. You can write it as x 1 plus x. Do not simply write it as 1, then you lose all information about x, and it will give rise to a divergence here. So, this is equal to 1 plus h cross omega by k T, and this is minus 1. So, 1 will cancel, and we have a half h cross omega by k T plus a k T. Now, given that this is much smaller compared to this, so we can write this U to be equal to k T, and that will tell you the C is equal to del U del T, which is a constant. Okay. And this constant in is coming out to be k, because we have done it in 1 dimension, but if you do it in 3 dimension and put in this capital N, so that this the total specific heat would be equal to so there will be 3 n k T, and this will give rise to 3 R. So, including dimension and number of particles. This is an expected result, because this result tells you that this C equal to 3 R, which is a constant, is called as a Dulong and Petit law. Okay. And at low temperature, you have to do something else, which is what we will discuss later, and this result gives bad. So, in the sense that this approximation becomes bad, which means that Einstein had gone wrong somewhere, which later Debye came and corrected it, and he said that not all the oscillators they vibrate about the mean position with the same frequency. So, there is a distribution of frequencies with an important cutoff, which is called as a Debye frequency, and once when he did all that, that is This is not a single omega that is coming in the picture, but there is a distribution of omega, and repeated the same calculation, which is what we will do when we do quantum statistics. We will see that the low temperature specific heat of solids or the contribution coming from phonons is T cube. Okay. So, this called as the famous T cube law of Debye. So, it is a Debye's T cube law of specific heat. So, let us do one more example of this canonical ensemble. It is a paramagnetic system of spin j. Okay. So, how is it different than what we have done earlier? We have done a spin half. So, spin half done earlier. And so, what we do is that we write down the again the energy is equal to minus g, we will just tell you what this g is, and then maybe there is a mu 0 or mu b depending on what you write. You can write it as h or you can write it as b. So, I equal to 1 to n. So, there are n spins, spin j, and these are written as, say for example, we still write it as sigma I, not meaning that they are Pauli matrices, but they just spins. So, each sigma I takes values between minus j to plus j. Okay. So, this is the problem that we have. So, we have to calculate this partition function, which is nothing but this summing over all possible values of sigma, and this is nothing but exponential beta g mu 0 h sum over I to n. See this I, it was written as j in the last problem, it just does not matter. I mean just a dummy index to say that these are the particle indices or the spin indices or the oscillator indices and so on. G is called as a Land-G factor. You can, it is not important to consider it here, but once when we talk about spin systems, we write this, it has a value, on screen value is equal to 2. So, this is the partition function that we have to again calculate in the closed form, and this is slightly difficult than the one that we have done, where spin half has only 2 values, which we have to just add over 2 values, but now there are 2j plus 1 values. Okay. So, the sum has to be done over 2j plus 1, and this is like a so sigma 1 from minus j to plus j through 0, basically you understand, minus j, then this minus j plus 1, and then it is 0, 1, 2, and then all the way up to plus j. Okay. So, these are the 2j plus 1 values that you have to sum over. Okay. And this is a little tricky, but not much. So, it is mu 0 h sigma 1, and then we have another one for another bracket for sigma 2 equal to minus j to plus j exponential beta g mu 0 h sigma 2 and so on. Okay. So, now in order to calculate this, you just have to do it like this. Let me just write this as exponential minus. So, each one of them will be identical. So, we will have to calculate one and then raise it to the power n, and let us see how we do that. So, what we do is that we write this as this z as exponential each one. So, let us write it as z 1, and we make this thing clear that this is like z 1 to the power n where n there are n spins there. So, n spin j objects. All right. So, this is equal to minus sigma y, and then this k is equal to so this can be written as minus j y, and then we have a k equal to 0 to 2 j, and e to the power y by whole to the power k, where y is equal to beta j mu 0, and what have we used? We have used h. So, beta j mu 0 h, which is equal to j mu 0 h over k t. Okay. So, this is each one of the sum, and this is so this is one term, and there are 2 j terms. Okay. And because it is inside the exponential, so this makes it a 2 j plus 1 term, and so this is equal to exponential minus j y given by that, and this is equal to exponential 2 j plus 1 y minus 1 exponential y minus 1. And what you can do is that you can do a symmetrization, that is, you can divide this by j plus half. You can take this 2 common and then divide numerator and denominator. So, that will give you just one step here. So, this is equal to exponential 2 j. Okay. So, when you do that, you lose this 2 j, and then you write it in a symmetrized form. It is j plus half y minus exponential j plus half y. So, there is a minus sign, and then exponential y by 2 minus exponential minus y by 2, and this finally gives us a closed form such as sine hyperbolic j plus half y and sine hyperbolic y by 2. Okay. Now, for j equal to half, which is what we know, this sine hyperbolic y. So, if you put j equal to half, so half plus half equal to 1. So, it is a sine hyperbolic y divided by sine hyperbolic y by 2. Now, use this as sine hyperbolic y is 2 sine hyperbolic y by 2 cos hyperbolic y by 2 divided by sine hyperbolic y by 2. This is equal to 2 cosine hyperbolic y by 2. This is what we have gotten earlier. So, this result is correct, and we get this j 1 to be equal to, or z 1 to be equal to this. Okay. And let us then write down the entire thing in our notation. So, the total z is equal to this sine hyperbolic beta mu 0 g, there is a g there as well. I probably have forgotten a g here. So, there should be a g here and a g here. Okay. So, g mu 0 h into 2 j plus 1 by 2, and then there is a sine hyperbolic beta g mu 0 h by 2. And so, this is the partition function that is calculated in the closed form, that is for the n particles. And what you can do is that you can calculate the magnetization, and the magnetization is nothing but m is equal to 1 over beta del h of log z, without going through, I mean writing down explicitly the free energy, you can write this like this, and this is nothing but n g mu 0 j, and we write a function which is called as a Brillouin function. It is a g mu 0 j h over k t, and this b j function is called as a Brillouin function. And this is nothing but equal to a ddx of log and then the sine hyperbolic 2j plus 1 by 2j x divided by sine hyperbolic x over 2j or 1 over 2j into x. So, this is that function. We are not going into details of this function, but I mean when you calculate this this function explicitly, then this can be written as, so this b j of x is equal to 2j plus 1 divided by 2j cot hyperbolic 2j plus 1 divided by 2j into x minus 1 over 2j cot hyperbolic x over 2j, where x we have taken it as, in this case we have taken it as x, or you can write it y also. It is like mu 0 j h over k t. Okay. We have taken that as y, you can write it as y as well. Okay. It is the same thing. So, let us now you can do an expansion for this large T limit can be obtained where you have mu 0 j h is less than k t, which means k t is much larger than mu 0 j h. In that case your x is much smaller than 1, and a cot hyperbolic function with the x is like 1 plus x square by 2 divided by, so that is like this cot hyperbolic is 1 by tan hyperbolic, which means that tan hyperbolic is sine hyperbolic by cos hyperbolic. So, this is cos hyperbolic by sine hyperbolic. So, you keep these terms there, and when you do a bit of simplification, you have other terms also for small x, because we are trying to look at the large temperature limit, and this thing a little bit of algebra would tell you that it is equal to 1 plus x square by 3. Okay. And other higher terms will be there, okay. But that is not important because we want to just consider this limit of x to be small, and then if you put this into this the Brillouin function and calculate the magnetization comes out to be some n into j plus 1 into g mu 0 square h over 3 k t. Okay. And there is a nice and close result for this at least at large temperatures, and that tells you the susceptibility which is a measurable quantity in magnetic system. This can be written as del m del h, okay, and this is equal to n j into j plus 1. It is a linear in h, so it is doing a derivative is very easy. So, this is mu 0 square divided by 3 k t, and you see again we land up with a result where chi is a function is 1 over temperature, and this is called as a Curie's law. All right. So, this is something that we wanted to do. We have done a number of examples. We have done a classical ideal gas, we have done a spin half system, we have done a spin J system, we have done oscillators, which is a model for solids, and this pretty much in normal sort of course on statistical mechanics, these things are covered, and one learns how to calculate the partition function in a closed form and hence use it to obtain physical quantities like for example, here magnetization or the susceptibility or deriving the equation of state for a gas or using the specific heat for a solid, which is a known problem, so on. And the last thing that we do here is the equipartition theorem. We have told the result of equipartition theorem, but let me just do a quick derivation of that. It is not difficult, but it is an important equipartition theorem. And as the name suggests, so this the energy at a temperature T is equally partitioned to all the harmonic degrees of freedom. That is not clear from the name, but it means that at an equilibrium temperature T, each harmonic degree of freedom will have an energy half kT in one dimension, and so per degree of freedom. So, the 2 degrees of freedom, say p square and x square, you will have half kT and half kT in one dimension. So, that will give you a kT. In 3 dimension, it will give you a 3 kT. Okay. So, we simply again do it for free particles. So, this E is equal to h p square p I square by 2 m. So, that is a sum over I, and then we calculate the average energy. And the average energy can be obtained as say epsilon I. So, this is what we write it as sum over I epsilon I, and this is equal to. So, we will have to weight this energy by the Boltzmann factor and divide it by this something like the partition function. So, that is a minus infinity to plus infinity exponential minus beta E. So, all these coordinates q1 to qn, p1 to pn, and then this epsilon I, and then all these d cube q1, d cube qn, and d cube p1 to d cube pn, and so on, and then we have to just simply divide it by exponential minus beta E and this d cube this integral minus infinity to plus infinity for each one of them. It is actually a 6n dimensional integral, even though we have written as 1 here. So, it is d cube q1 to d cube qn and d cube p1 to d cube pn. Okay. So, that is the quantity that we have to calculate, average energy at a temperature T. And so, what we do is that we sort of separate out these energy, the total energy to be equal to which is a function of course of all these q1 to qn and p1 to pn, and this is equal to epsilon I p I plus E prime. So, we have separated out all energies excepting the the component that we want to calculate the average for, and writing everything else as E prime. So, we will have this E prime as or rather this epsilon I average. We have used this form of average, or we can write it as up to you, you choose your notation. Okay. So, this is equal to So, minus infinity to plus infinity, exponential minus beta epsilon I plus E prime, writing down the total energy, and then there is a epsilon I and there is a dpi. Now, why I write only dpi? Because this only ei depends upon pi, and then of course, you have d cube q 1 all the way up to d cube q n, and then d cube p 1 to d cube p n. But now, remember that 1 is missing. So, d cube p I is missing because I have already written that, is missing from this, because we want to calculate for a given particle which are labeled by this indices the average energy of that particle, and this is minus infinity to plus infinity. It is exponential minus beta epsilon I. So, now you have a dq q I 1 to n and dq p 1 to dq p n. Okay. We just have because there is no distinction between any of them, but what we can do is that we can write this down as a minus infinity to plus infinity exponential minus beta epsilon I dpi and exponential minus beta e prime and d cube q 1 to d cube p n, understanding all the things are there, and we write it with a prime summation, because this prime summation does not include a pi integral which is separated out, and similarly we write this down as well, epsilon I dpi and an integral which is exponential minus beta e prime d cube q 1 to d cube p n. Now, you see that these two integrals would cancel each other, because it is all everything is common there in the numerator and the denominator, and you are only left with this part, which is nothing but you can get an epsilon I out by taking a minus del beta of this minus infinity to plus infinity exponential minus beta I dpi and divided by these exponential. So, again from minus infinity to plus infinity, and we have this exponential minus epsilon I dpi, and this is equal to minus del beta of log of minus infinity to infinity exponential minus beta epsilon I dpi, and so I converted this into a minus del beta of log of this, because if you take a del beta of log of this, you will get this term that is in the denominator, and you also would get this term in the numerator. All right. So, we are almost done. So, this epsilon I average, which is per particle, the average energy per particle, is nothing but equal to, so we can calculate it equal to 1 by root beta minus infinity to plus infinity e to the power y square by 2 m dy, where y we have taken it as pi into root beta. Okay. So, that this is the average energy per particle at a given temperature T, and this root beta has come out. We have just written it a little sort of familiar fashion, so that we can apply this Gaussian integral directly. Okay. So, this tells you that log of this minus infinity to plus infinity. So, we have just done some sort of simplification here, but it may not be so much required, because is exponential minus dp beta I dpi, this is equal to minus half of log beta and plus some log of this quantity, which is we do not really need, because this is like it is independent of the temperature. Okay. This part which we have written there. So, this is equal to I mean this is really equal to that minus infinity to plus infinity e to the power minus beta p I square over 2 m, that part. Okay. So, which is this part, which is the second term here. We have nearly solved the problem. So, epsilon I is equal to minus del beta, writing it once again. So, this is equal to del beta of minus half log of beta, which is equal to 1 over 2 beta, which is equal to 1 over 2 k T. Okay. So, this is an important result, that average energy per particle is this for n particles in 3 dimension epsilon I is equal to 3 n by 2 k T. Okay. So, this is the average energy per particle. Now, I have also said that it says that per harmonic degree of freedom. So, for harmonic oscillators we can simply add another contribution because of that x squared degrees of freedom. So, this becomes equal to which we call as the internal energy is equal to 3 n k T, okay, or 3 R T. And this is precisely the reason that the specific heat of solids comes out as 3 R, which is called as the Dulong and Petit law. This is an important result in statistical mechanics or thermodynamics, and should be kept in mind that this is a classical result, because we are talking about a temperature at a given temperature T, and you see that all the results that we recover are those at large temperature, that is when the thermal energy dominates in the system. So, we will see one more theorem in the next class called as the virial theorem. We will stop here today. Thank you.